They seem to get things like within minutes. I don't know who's doing that, but I mean, as soon as it's posted to iPod. Okay, here we go. Sorry. So welcome to, where are we? This is Introductory to Astronomy, Physics 1600, and I'm just waking up. And this is the third lecture. So welcome. There's people in the studio audience for the actual lecture, but you may be watching this decades from now, wondering what happened back then. You know, what were the late 2000s about, or 2000 aughts about? But anyway, let's think about what is on the screen here. So today's informal quiz is, what's this? So we've already had some speculations from the studio audience, and this will be revealed during this dramatic lecture in lurid detail. So let's get to that lecture. But first, the obligatory slides, without which people would be lost. So this is Introductory to Astronomy class. This is lecture 3, universe, scale, and light. So we're still on light. So we'll be reproducing some of the things from last lecture, which is repetition, which in my view is somewhat good. So this lecture is originating from the studios in beautiful Michigan Technological University. I am the not very beautiful Robert Nemiroff, who is your professor for this course, who will be explaining the oddities of the universe to those who want to hear and those who want to get credit. If you want to get credit, I strongly advise going to courses.mtu.edu, because if you only come to class or if you only see the videos, you will be greatly enlightened, possibly, but no one will know, you will not receive college credit for that. One advantage of this course is that it can be taken only online. You don't have to get credit, you never have to come in and be here. You can just stay home in your pajamas with your fluffy slippers and get full credit. How many other courses can you do that with? And not only that, this is the only class where you not only can stay home with fluffy slippers, you cannot spend a lot of money. In fact, you can spend almost no money because you don't have to buy any textbook for this class. What you're responsible for is the lecture material, as you see here, in class or over the web, through iTunes, through learnoutloud.com. In place of the textbook, I'm including not only material here, but which Wikipedia entries. So I will explicitly say which Wikipedia entries you're responsible for. So if something appears there that I forgot to mention, you might be responsible for it, but you don't have to memorize it, because you can always go back, given a quiz or a midterm or a final question. You can go to those Wikipedia entries and look them up. You'll know which ones they are. It won't be all of Wikipedia. Higher math is not required for this course, so if a Wikipedia entry goes into integrals or differential equations, don't worry about it. You're not responsible for that. You will also be responsible for the astronomy pictures of the day, APODs, posted during the semester, all the way from September 1st through, I think, December 15. And I will cover them each week, 7 at a time. So today, at the end of the conclusion of this lecture, do not get up and run out, because you will be treated, let's say, to the 7 most recent astronomy pictures of the day, some of which have very topical things going on in astronomy and astrophysics today or recently. Not only do you need to go to courses.mtu.edu to get credit, it would be useful to actually take the quizzes and the midterm and final when they appear. It will be listed when they appear. It says when they are due. If you wait for the last minute, you could be cutting it close. Please don't cheat. I expect everyone to do this themselves. We have ways of knowing you cheated. Okay. So the Wikipedia entries that you will explicitly be responsible for are, you type these words into Wikipedia, the English version of Wikipedia. Black body, spectrum, spectral line, Bohr model, and Doppler effect will be all going today. None of these has really, really long Wikipedia entries. All right, so a little bit of review from last time, but let's go through it. The black body spectrum. Everything emits light, and not only one kind of light. So me, I'm proud to emit light. I emit mostly infrared light. So when you look at me, you're not seeing the light I emit. You're seeing the light I reflect. if you look at me in person. If you look at me through your computer monitor, you're seeing the electrons hitting your screen and emitting light, and that's different. But supposing you were here in person, you would see me. There are lights in this room, and these lights illuminate most of the room. They bounce off many things, including me. So that's the light you're seeing. However, if your eyes saw infrared light, then you would see a little bit of reflected light because surely enough the lamps in the room emit infrared light. But if you go far enough into the infrared, which is more red than the average human can see, you will see that I glow. So if you were to turn off these lights, the room lights, you would see that I continue to glow at the same brightness. And I don't only glow at one temperature. I am also giving off visible light. It's just that I'm giving off such little visible light that it's very hard to tell. So when your eyes are seeing in this room is you're seeing the reflected light, mostly. There's a tiny little bit of visible light. The peak energy, peak wavelength that I emit at is in the infrared. So what color am I? I am infrared color, and so are you. But this course is about astronomy. It's not about me. As much as I'd like it to be about me, it's about astronomy. People don't pay to hear about me. They hear about stars in the universe. So we'll go with that. So stars, they glow so brightly that when you look at the sun, you're not looking at the reflected light of anything. You're looking at the light of the sun. And the sun is very bright in visible light, and you see that. When you look at things in the solar system, for instance, the moon, as I will repeat, the moon, you're not seeing the moon's own light. The moon does glow. It's pretty cold, though. The moon does glow toward the colder end of the infrared, but the brightness you're seeing is reflected sunlight because the sun is so bright. So let's say you're looking at the moon when there's only a thin sliver, when it's in the crescent mode. What about the rest of the moon? Because if you look really hard, the moon is not only the crescent. You can sort of see the rest of the moon. Maybe that's the moon's infrared glow. And the answer is no. What you're seeing is light emitted originally from the sun, reflecting, let's see, how does this work? It bounces off, let's see, you're seeing it bounces off the Earth and then off the moon and then comes back to us. So part of the Earth is lit up pretty brightly. And so the part of the moon that you see glow is then, it's all sunlight. Now it's bouncing around between the Earth and the moon like a pinball, but you're still seeing essentially sunlight. You need special glasses to see into the infrared. Now, the military has these glasses. So it turns out that the military, which actually borrows a lot from astronomy, one of the things that drives astronomy is military funding. The astronomy, it turns out, is really good at determining what time it is from looking at the sky, determining what your longitude is. So classically, the military, when they had ships on the sea, they turned to astronomers to find out where stars are because that would tell them where they are on the globe and what time it is. But more recently, astronomers like to look at the sky in many different wavelengths. They like to look at the sky in infrared and gamma ray. And so the military has then developed their own technology, but they look to the astronomers who've already developed technology in, say, looking in the infrared. And they adapt it to Earth technology. So now many people in the military, I understand, can wear these kinds of glasses strapped to a helmet which allow people to see in the infrared on the battlefield. And then you can fight at night. So everyone else, they're looking for reflected sunlight. But they figured out that people glow. You can't stop people from glowing. Well, you could put them in something cold tank, but most people glow. It's expensive to do that. And therefore, you can see people at night on the battlefield, and then you don't have to stop fighting during the day. In fact, sometimes it's better to fight at night because the other side can't really see very well. And the astronomers' inquisitiveness as to what the night sky is like in redder than we can see is turned into useful battlefield things to know. Stars, it turns out, glow. The sun glows mostly in regular light, but there are stars that glow mostly in infrared light, and planets glow in infrared light. So when a star glows, it doesn't only glow at the one temperature that it appears. It's possible to see only in one temperature. There are lights. These lights aren't those kind of lights, but there are specifically the kinds of lights that, fluorescent lights. Many of those glow only at very specific colors because they have, let's say, sodium lamps or sodium in them, and they only glow in just sodium light. But these lamps, they glow across the electromagnetic spectrum, peaking at some wavelength, and so do we, and so do most things. So when something has a black body glow, it doesn't only glow at one wavelength, it glows at many wavelengths. It just, as we see from this graph, which has wavelength here, as opposed to brightness here. So we see that something that has 5,000 degrees similar to the sun glows like this and has a peak wavelength, but it emits light at every wavelength. Very little down here and very little up here, so it's mostly here that it glows. Now if you cool it down to only 3,000 Kelvin, then the peak wavelength moves over and its black body temperature appears more red. So this one appears even more red. So this one, they are characterized, caricatures as blue, green, and red. But you can see black bodies glow across the electromagnetic spectrum. Don't worry about this one right now. So I glow and you glow across the electromagnetic spectrum. You glow in blue light, you glow in more blue than we can see, you glow in X-rays, but not very much. You glow mostly in infrared light. So how do we know? Let's say we want to break things into its specific wavelengths. It's just like last lecture, you can use, there's many ways to do this. One way is to just use a block of glass. But if you use a rectangular block of glass, you don't see anything cool. So you put that one down because people are bored. Then you pick up a more interesting block of glass, and that is a prism, which is a triangular block of glass. And then light comes in one direction. Because different color lights have different speeds inside the dense glass, they go over here, and then they come out in different colors. So if you were to take, let's say, this light here, and you were to hold up a prism in front of a background, you wouldn't see colors. So you need a narrow band of light to come in. Then you see colors more easily. There are other ways to see colors, and here's one way. Sometimes if you look up at clouds, and this is pretty rare, so this isn't your average cloud, you can see colors just up in the sky. So let's say you're looking up, and here's your basic building over here, which is boring. That's B-O-R-I-N-G. And then you look over here, and you see a cloud, thin clouds. And you keep looking because it's interesting. So building's boring, sky is interesting, which happens a lot, which is why we have classes like this. So why is this? Now, most clouds don't do this because most clouds are water drops. So you can fly through clouds. You've been on planes, planes fly through clouds. A couple hundred years ago, they didn't really know this. So they were afraid of clouds, more afraid of clouds. But it turns out when there's fog on the ground, you're in a cloud. And you walk around, and the thicker the cloud, the less you can see. So clouds are fine. Planes can fly through them. Cars can drive through them. You can walk through them. Clouds are tiny little water droplets. Now, if many of these water droplets turn out to be just about the same size, which is somewhat rare. Clouds are many different water droplets. So because all the optical effects clouds do, we usually turn them white. If, however, the sunlight's in the wrong place and you can't see through the clouds can appear gray and even dark gray. This cloud is called an iridescent cloud in the sky, and it has many water droplets that are about the same size. What causes that? People aren't really sure. There's some mechanism, some kind of winding mechanism or falling mechanism that causes a bunch of the cloud to be most the same size. Then light comes through here and does something called diffraction, which we won't discuss a lot right now. And the diffraction through all these water droplets of the same size causes a prismatic effect, which causes rainbows in the sky. Now, you can have rainbows just out in, I should have included a rainbow. If it's raining, in one part of the sky and it's sunny in another part, and you turn around and you look toward the rainy part, many times you can see a rainbow. And a rainbow is light reflecting off of lots of water droplets again and gives you a prismatic effect. You can create your own rainbow when it's sunny out. You can just get a garden hose and spray in the direction, spray opposite the sun and look opposite the sun, and the sunlight will reflect and refract off of the raindrops, the water drops in your spray from the hose, and you can make your own rainbow. Okay. So we're getting close to the first image here. Stars, it turns out starlight can be passed through prisms. It can be passed through iridescent clouds, but that's harder. It's easier just to put a prism on your telescope. So actually there's things, well, to a prism on your telescope. So they've decided to do this. And they started doing this more than 100 years ago. And so they get the spectrum of stars. So some stars are bright and blue. And here you see not much red, so these are, but lots of blue. A little bit of yellow. Then you get other types of stars, and A-type stars are here, and they have less blue, brighter in the blue-green, brighter in the red. As you go down, they've labeled them. So this is O, B, this is A stars, these are F stars, these are G stars, K stars, and M stars at the bottom. So our sun is a G star right here. Yay for G stars. This one band is one type of G, and this is a cooler type of G star. So I'd say our sun is probably closer to the cooler type of G star, and its peaks mostly in the green-yellow, as we keep repeating again and again, as if there's something wrong with me. As you go down to the M stars, it peaks more in the red. But you might notice that the spectrum is getting kind of dirty down near the bottom. Is this because the prism is dirty? Well, no. If the prism was dirty, the dirt on the prism would pretty much affect all light equally, assuming it's big drops of grime, of dirt. But the reason why the M stars here, the M stars, it turns out, are cool, and they have a lot more of atomic and molecular atoms in them, and these atoms absorb starlight. And as they do, they absorb very specific types of starlight, and they drop out a very specific color. So a specific atom or a specific molecule will be excited, will have its electron jump up when hit by a very specific color, and I will review this in a few more slides. And that will knock out that color. Now, since there's not all that much atoms and molecules, most of the color gets through, but some of that very specific color gets absorbed. So you see these here. These are lines. These are absorption lines. So there are lines missing. And these missing lines tells you that there is some kind of element, atomic element in that star, in the atmosphere of that star, that's absorbing this. So you got something for free at this point. You went to look at the colors of different stars, and you found out that these stars are slightly missing some colors. And you can find out things about those stars by, well, those are gases. We have gases here at Earth. Let's see if we can mimic finding those absorption lines here on Earth. And usually we can. And therefore, we can tell things about stellar atmospheres just from not only how that they emit black body radiation. This black body has a peak color, which tells us how hot the surface of the star is, but it also, from the absorption lines, tells us what elements might be on the present in the atmosphere of the star. So absorption lines again. Gases absorb very specific colors of light. Different gases, different elements absorb different colors. Hydrogen, for instance, the most abundant element in the universe, emits very specific colors which we know because we have hydrogen here on Earth. So we go to our labs and we put on our silly lab coats and we put on goggles because that's the safe way to do things. And we shine light into hydrogen, and we find out that, yes, hydrogen is absorbing very specific kinds of light. And then we go to look at the spectrum of stars, and we see those exact same colors being absorbed. And that tells us that stars have hydrogen in them. Then you look at stars, and you look at the sun, and you see that there are other dark lines, not just hydrogen. And you say, hey, wait, I thought stars are all hydrogen. But no, there are other lines that are in the atmospheres that are absorbing these things. And so when they did this for the sun, so the sun's the brightest star, right? So the sun also gives off lots of photons. With stars like Sirius and dimmer stars, we're photon-starved, and we have to use big telescopes to acquire lots of photons in order to analyze them. That's why we have these big telescopes all over. That's why we launched the Hubble Space Telescope, and why we'll be launching the James Webb Space Telescope in space, because they have big mirrors, and big mirrors essentially make your eyes really big, collect lots of light. Sun's not like that. Sun's got light to burn. It's got zillions of photons just zipping off it. Usually you have to block light from coming into your detector because the sun has so much of it. So you can see lots of lines in the sun. And so they looked and they saw some really strong absorption lines in the sun, and they didn't know what that was. What is that? We see these absorption lines in the sun, we don't know what it is. So they go into the lab and they say, wait, it must be some kind of element. And so they determined that there was an element that they then found here on Earth, and that element is helium, which helios stands for sun. I'll write right over this because I'm not proud. Helios is a term for sun. So helium, which turns out to be the second most abundant element in the entire universe, was generally unknown on Earth until matched with lines from the sun, and so they named it helium. It's an exciting, it's always cool. I always like the way things get discovered, because things get discovered in strange ways. Science is not what we call a linear process. You don't go usually go through steps 1, 2, and 3, and then you discover what you expected in 1, you discover what you expected in 2, and you discover what you expected in 3. Science doesn't work like that. Science has, you look at 1 and you found something in 1, and then there's something strange here. And at first you ignore it because it's strange, you didn't expect it. And then maybe later you come back and you look at it and say, hey, what was that? So they looked and they found hydrogen in the sun, and there was all these lines, and they said, oh wait, maybe that's something else. And so they discovered helium. And so then they start focusing on helium, saying, hey, helium's really great. Turns out helium is really great. Helium doesn't burn anywhere near as easily as hydrogen. So if you want to fill up your Goodyear blimps at the dirigibles in the beginning of the century, were filled with hydrogen, and that didn't work really well. Because even though you have safety inspectors, and they make sure the hydrogen is in there safely, things can go wrong. And if you have oxygen from the normal atmosphere and the hydrogen in your balloon or dirigible and a spark, boom. So that's not good. So they found out that helium floats. Helium's lighter than air. You can fill your dirigibles with helium, and they will float, and they will not catch. If you put sparks in helium, doesn't matter. It then turns out that airplanes are much better military devices than dirigibles, because dirigibles are slow and can be shot down easily. But still, you can use them for advertising because they can hover over stadiums. The U.S., I think, is one of the main suppliers of the planet of helium. We have helium mines that helium has distilled out from the Earth, like gold and copper here in copper country, places where helium is distilled out. And so we leach it out from the Earth and save it. So the United States actually gets a lot of helium. Here we are. This is a spectrum. So someone guessed spectrum and they were right. And these are elements. Someone else guessed that. This is the sun. This is what happens if you take the sun and you put it through a prism. You get tremendous amount of detail because there's so much light. So you find the sun is really bright in the green and yellow, like I keep saying, like there's something wrong with me. Then you find there's even light in the blue because the sun is a black body and emits light across the electromagnetic spectrum. So it peaks here, but it has lots of this and lots of this. And then you find there are bright absorption lines, and some of those are hydrogen. And then you find there's other bright lines, and some of those are helium. And then you find there's lots more lines. What are they? So, show of hands, who thinks that we understand all the absorption lines in the sun today? Okay, who thinks that's a trick question? I wouldn't be asking that. So if you actually go to this apod right here, you will find that we don't know. Even today, modern science knows everything, right? You're just here to learn, just here to learn science. Scientists come up to the front, teachers come up, and they just tell you what we know, and then you write it down because we know everything. That's not true. We don't know everything. We don't even know all the spectral lines in our sun. There are things, what's this one? I don't know. So you go into the lab, you try to create stuff, yeah, get something about that, but maybe some other ones too, and we're not sure. So many of these lines have now been identified, but not all. It's not really all that important, we think. There's cooler gas hovering above the sun with very small amount of trace elements, and it's not all that scientifically important to know what they are. So it's not one of the biggest quests in modern astronomy to find this. But I think it's really cool that an object as common as our sun emits light that we see every day and bounces off of everything. And there are little notches. There are holes in that sunlight, places where not so much color comes through, and we don't know what's causing all of that. So it shows that science doesn't know everything. Science knows actually just a little bit, and many times pretends to know a lot more than it does. And we don't know why many colors of the sun are missing. To explain why some colors are missing, we need a simple model. There are complex models that deal with sophisticated quantum mechanics that have things like the Schrödinger equation and things like that that are complicated and involve higher math. But there's a simple model that pretty much explains things as far as we need to know them here. And we know this model is flawed, but we like it because it's easy to visualize, and it gives approximately some right answers. So like Newtonian gravity gives pretty much right answers. Now Einsteinian gravity, general relativity, gives better answers. But it's too hard to compute things in general relativity. So usually we just, for common things, Newtonian gravity is fine. So for many things, the model of the Bohr atom is fine. So the Bohr model was created in 1913, which you might notice is still less than 100 years ago today. So I'm always amazed that much of what we learn happened in the lifetimes of your great or great-great-grandparents. So in this simple model, you have electrons orbiting a central proton. Now I have a plot coming up. So here's your proton. I don't like that one. Here's a P. And now around it, there's an E. So the P is positively charged, and the E is negatively charged. So the E likes to be near the P because opposite charges attract. But it goes in an orbit around it. So it can't go to it because it's got too much momentum. Now, that's not really the quantum mechanical way of thinking about things, but that works well enough for this. Now, it turns out that for reasons the Bohr atom doesn't easily explain, there are certain orbits that are allowed. In this model, it's a lot like the planets orbiting the sun. In reality, as I keep saying, atoms and molecules are not like planets orbiting the sun. We now have more sophisticated models. But this is good for now. So there are certain orbits that are allowed. Electrons, more electrons orbit many protons and neutrons. Neutrons have no charge. So they orbit. Now, let's go to the next one. Electrons can jump up and down. So here's a proton in the center. And these are electrons. So the proton is in green. The electrons are small blue. And there are 3 allowed orbits in this picture of the Bohr model of the hydrogen atom. Hydrogen just has 1 proton in the middle. So here we have a n equals 1 electron going around that. And here's an n equals 2, a further out orbit. And here's a n equals 3 further out orbit. And the neat thing about the Bohr model is that, let's say an electron was to jump from the n equals 3 to n equals 2, to jump on this path. Well, it would just jump down really quickly. It would emit light. And it would emit exactly a very specific color of light. Perhaps in this one would be in the red range. So when this happens, it would be a very, very specific color of red that would be emitted. Now, if you were to have red come in just like that and hit this electron, it would jump back up from the n equals 2 orbit to the n equals 3 orbit. And this way, there is absorption and emission of light. And it's very easy to see in the Bohr model. Now, there's different kinds of spectrum that we'll talk about now, 3 types. So we have the background now to talk about 3 types. One is just a black body without any gas around it. So it is an idealistic thing. And then we pass the light from that black body through a prism, and you get what's called a continuous spectrum. Continuous spectrum has no absorption or emission lines. So another way to do it is then you have this emit some kind of hot gas. So you have a hot gas, and this hot gas has, let's say, hydrogen in it. Let's say it's just hydrogen gas. In the hydrogen gas, it's hot. Atoms bumping into each other. As they bump into each other, the electrons jump up, and then they get they fall back down and emit light, and this light can go through a prism, and then you only see emission lines, only emission lines. Now, let's say you were to take a gas, let's say a cold gas, and you were to put it in front of this light previously, then you will see the continuous spectrum, but now the light from the thing, very specific colors, much of that light is absorbed by the cold gas in bumping up those electrons from low energy levels to high energy levels. And so that light is taken out, and you see dark lines like we see with the sun and the stars, absorption spectrum. So emission lines, they're the same colors as absorption lines, except they are bright instead of dark. The emission lines, an emission nebula. So there are whole nebula. So now let's go out to the sky. This is supposed to be a beautiful astronomy course, and we've seen not too many beautiful pictures yet, but we will see them very soon. One of the most common things you will see on the sky are emission nebula, and they glow in red light. They glow in hydrogen light. So they're being excited by nearby stars and emitting red light. Most of the time you see bright hydrogen alpha, where the electron falls from the n equals 3 to the n equals 2 level. So this is one. Here are bright stars. These stars are mostly, they're brighter than the sun. They're mostly blue. Light from these stars is traveling out here. And around here there's hydrogen gas. This hydrogen gas is relatively cold. Now the light is hitting the hydrogen gas and exciting it, knocking the electron to a higher energy level. That electron then falls back down and emits red light. It doesn't know where we are. So it can't emit red light right toward us, so it emits red light in every direction. And since we're in one of those every directions, we see it. So this is the Rosetta Nebula, and it sort of looks like a rose. The stars in the center have probably supernovae, but also stellar winds that are pushing out all the gas from the center. But there's still lots of gas out there, and we see it as an emission nebula. So here's another open cluster of stars, lots of bright stars. And the light from that stars is hitting the hydrogen gas, which would otherwise be invisible. And we are seeing it in red light. We could also see it in other colors that hydrogen would emit, but our eyes are particularly sensitive to red light. Here's another one. Okay, so this is a reflection nebula happening right near here, so it's purple. So there's small things called dust grains, which are not the dust you see around the house. They're smoke-sized dust, dust grains that occur mostly in the outer atmospheres of stars. And here's a dark nebula. So this is absorbing most of the light from behind it. You usually can't see through it. They're opaque. But as you get far enough away, you don't see the blue of the reflection nebula. You see the red of the emission nebula. So this is emission, and around here is reflection. So it's reflection because the reflection nebula is blue because most of it is reflecting off of dust grains. And so reflection itself, like the sky is blue, many times makes blue things. And also, you're reflecting the light of a blue star. So those things combine to make blue reflection nebula. The emission nebula, though, is hydrogen usually, with the electron bouncing down from the 3 to 2 level. One of the great things about modern astronomy is that expensive equipment is becoming more and more visible, more and more buyable by the amateur. So there are relatively affluent amateurs, but almost anyone now can afford a charged coupled device, a digital camera that's sensitive enough to hook up to a telescope. And you can look it up to a telescope and look with really wide fields of view. So very powerful telescopes have only narrow fields of view, small parts of the sky they're looking at. But the amateurs are now able to look at wide fields of view with sensitive digital cameras with CCDs in them, and they can pick up all this background glow that we didn't really know existed before. And so if you look toward the belt of Orion, you can see not only the Horsehead Nebula, which is well known, but now you can see all these wisps, which are emission nebula, emission of hydrogen just floating around in space, a couple hundred light years away. Okay, one more topic before we go, and that is the Doppler shift. I didn't know where to fit it in, so I'm just sort of going to staple it to this lecture. Doppler shift is important. Everyone's heard it, but not everyone's understood what it is they're hearing. So you usually will hear this sound every day, when let's say you walk blazingly across the street and the people who you walked in front of are pissed, they will honk their horn, and as they go by you, it will go doo. And the higher shift when the car is coming toward you and threatening to hit you is the higher pitched Doppler shift. So that's being shifted toward the higher end of your hearing range. And when it goes past you, you can't hear their cursing because their window's up, but you can hear their car horn, and that will now sound with a lower sound because it is moving away from you. So the higher pitch, they're both Doppler shifts. When it comes toward you, you're hearing the higher pitch of the horn, and when it goes away from you, you hear a lower pitch of the horn, and if the car was to stop and sound their horn, it would be in the middle. So the shifting to the high and low is the Doppler shift. This happens with light, too. So if you have a flashlight that, let's say, emits green light, you look at it and you'd say, wow, that's a bright green light. You were to shine it, it would illuminate things, walls with green. If you were to run towards somebody, that green light would be shifted toward the blue end of the spectrum, and that would be a Doppler shift. If you could run fast enough, you could go bowling with a flashlight. Your flashlight would appear so blue, it would go into the X-ray and gamma ray range if you had run fast enough, and the photons would become more energetic, and eventually they would be energetic enough to knock down bowling pins. If you were to run away from somebody with your flashlight, it would appear more red. So when the light appears more blue, it's called being blue shifted, and when it appears more red, it's being red shifted. The photons, though, are always moving at the same speed, which is counterintuitive. They're always moving at the speed of light, which it's called. That was one of the great things that Einstein realized, that light always has the same speed. But it can have different energies. So even though it has the same speed, you can have blue light, which has high energy, and you can have red light, which has low energy. Okay, so this is a spectrum from a black hole, and there's gas going around this black hole. So this is an APOD from way back in 1997. And so when the gas is coming toward you, that light is blue shifted, and when the gas is at rest, it's sort of this color, and moving away from you, it's red shifted. So the gas going around this black hole, when it comes toward you, it's blue. It shows both blue shifting and red shifting, depending on what part of the disk you're looking at. Okay, so this will conclude the APOD. Don't move, though, because we're going to review 7 astronomy pictures of the day right after this. Next week, though, we're going to talk about observing stars and planets. Okay, so now I'm going to go to APOD. Here we go. So I will just review the way you get to APOD is typing apod.nasa.gov. And you will be taken to this web page, which shows you the current astronomy picture of the day for today. So we will come back and do this. I'm going to do these in chronological order. We're going to go back to next Thursday and do that one. So we can think about what this is, though. So let's go back in time to, I believe, this is last Thursday. So this is the astronomy picture of the day for last Thursday, September 4, 2008. And this is spokes of the Helix Nebula. So the Helix Nebula is a really cool nebula on the sky. So after the telescope was invented, people went out and they looked and they found nebula, and they found things that looked a little bit like planets because they were big, but they weren't planets, but they were still called planetary nebula. They are what happens to things like the sun after the sun in 5 billion years. The sun will contract and the outer envelopes of the sun will just go away, and it will create a planetary nebula. So this is the future of our sun. This star has been there first. And its outer layers, it creates these spokes, and people study these spokes. They're not all that well known what they are. But what we can glean from today's lecture is that there is hydrogen gas out here that is being lit up by the central, probably white dwarf. And the white dwarf is energetic enough to knock the electron out, and as it falls back, it emits the red light. So we're looking down the Helix Nebula. We're looking down the barrel of the Helix Nebula, which is more or less a cylinder. Okay. On to the next one. All right, this is just a really cool shot. So sometimes on APOD, we get really cool images submitted to us that we just love to run because they're really cool looking. Sometimes they're very educational, sometimes they're not. I don't know if this one is very educational. This one has Jupiter in it, and this one has the band of the Milky Way in it, and it has some strange looking clouds, and it has a road. So it looks like this road somehow leads out to the same destination of these clouds, which may in fact be this city, but that would be wrong. These are just things caught by coincidence. This was sent to us by one of the photographers that actually sends us many images. Teasel, I think is his name, or Tezel, and he's helped form and participates in a group called The Sky at Night, TWAN. I forget what TWAN stands for. I thought The World at Night, sorry. And they try to get cool foregrounds for interesting astronomical backgrounds. And the reason for that is because many times we at APOD were sent really cool things in the background, and we realized that there could be something cool in the foreground, but people didn't think to do that. So the way we told people we wanted to do that is we started, whenever we got an image like that, we would put it up, or many times we got an image like that, we would put it up, and people realized, including this group, that they can go around and photograph famous landmarks and really cool vistas with cool backgrounds. This is actually taken in Turkey. We're fortunate enough at APOD to be sent things from all over the world. So we've featured images from many, many countries, not just from the United States. And this one is from Turkey. This one, I think, is from New York. So this is from the US. What you're seeing here is an image, is a flock of stars, but it's not, these aren't really stars. This is an artistic license was taken here. These are birds. So why would the astronomy picture today feature birds? Birds are not themselves stars. One of the reasons is this shows what it might look like if we lived in a globular or open cluster of stars, where a lot of the stars had relatively the same brightness and there were lots more of them in the sky. We have only one bright star in the sky, and that's a little bit unusual. Most stars are members of multiple star systems, where there's two or many more. There's also open clusters which have 10 to 100 stars, and globular clusters which can have 100,000 and even more stars altogether. So what would it be like to live in a planet that has, in let's say, a globular cluster? You would never have true nighttime. But when it got relatively dark, when the closest stars are away from you, your sky would be lit up with many, many stars. There's a famous, many famous stories about things like that. My favorite is Isaac Asimov's story, Nightfall. I'll write that down. I think it's, you can purchase it on Amazon. There's a book by the same name that has that story, and it talks about a civilization where true night occurs only every few thousand years or so, and there's only rumors of what happened last time. And the people on that planet go crazy and they essentially destroy things because the rumors that the sky would light up with stars were true, and for some reason people in that society take that as a clue to sack all things technological. Okay, on to the next astronomy picture of the day, which is a rerun. We run reruns on weekends. And so many times we're asked, why is it you run things on weekends, images that people have seen before on weekends? So you can answer that just by going to the frequently asked questions, and you get there by going to the About APOD, then you go to the frequently asked questions, then we have that. Question 4, have some APOD pictures been run more than once? And I explain it there. But I will explain it in person now. The answer is manyfold. First of all, we're lazy. And we don't want to keep doing new ones all the time because it's a lot of work to do new ones. Another reason is because images need to be updated. Many times, our readership turns over. There's new readers to APOD all the time. And many of the newer readers haven't seen some of the best images in astronomy because they're old images. So if we never repeated, the newer readers wouldn't get to see the best images. So by rerunning the best images, we're showing people, here, look at this. That also gives us a chance to upgrade the image many times with a higher quality image because the bandwidth of the internet keeps going up, and the browsers, people are more and more used to looking at bigger and bigger images and even videos at this point, so we're able to include a bigger image without people complaining, and we're able to update the text. So sometimes the text goes a little bit stale. We can put in more recent things. We can put in sometimes a better understanding has become available. So yes, this was run before. This talks about searching for meteors in Antarctica. So meteorites. So when a meteor hits the ground, it's a meteorite. And many of them are found here in the US. Some are found here in the Keweenaw Peninsula. They're found all across the world. But if you find one, you're not sure right off that it's a meteor, right? You can say to your friends, look, I found a meteor, and they say, great. But if they might not really be convinced. Or then you want to go to, your local news people, and they say, well, how do you know it's a meteor? Well, it looks like a meteor. What does a meteor look like? Well, it's meteor colored. Well, what color is that? Turns out that it's sometimes hard to convince people. You actually have to look at meteors in very specific ways to find chemicals that aren't very common here on the Earth with them in order to prove that they're meteors. But so what happens is it turns out that most claims of unusual-looking rocks are not meteors, and that people get tired of testing them because there's so many common rocks that the true meteor is hard to find. But if you go to Antarctica, there's these vast sheets of ice where there's nothing there. It's just ice. And it's called blue ice because it's got a blue tint. So if you drive your snowmobile across the vast sheets of blue ice, sometimes you find a rock. Now, what would that rock be doing there? Turns out, real good chance it fell from space and it's a meteorite. So instead of picking up rocks from a rock field and testing them all, that's hard. It turns out to be easier to go to Antarctica and drive your snowmobile across the blue ice and pick them up. And people do that. And that's what these people are doing. And you can find some really cool meteors. Some we think are from the moon, so you don't have to go to the moon. You can actually go to Antarctica and find rocks that fell off the moon. How can they fall off the moon? Another meteor hit the moon, rocks were thrown into space, they orbited around the solar system for a while, and then they fell to Earth. And you can even find rocks that we think are from Mars. And we don't know what all the rocks are. Okay. So let's go to, on Monday's image, September 8th. The astronomy picture today was the spacecraft Rosetta is on the way to going to a comet, which is the name which I can never remember and will probably not pronounce well. It is comet Churyumov-Gerasimenko. So I'm sure you've just been discussing that comet with your friends. But so it's on the way there. There's a spacecraft launched by the European Space Agency, not by NASA. A lot is launched by NASA, but not this one. And so they decided to pass it by some other things on the way to that comet. And one of the things on the way is this asteroid, asteroid Steins. So other than knowing it's there and being able to bounce radar off it and knowing it's a speck of light in a telescope, we don't know much about this. So every chance we have to drive a spacecraft past an asteroid, we take it. So we took it, and here's one of the first close-up images. And it turns out this thing looks like a diamond. It's a 5-kilometer diamond, but it's not made of diamond stuff. It's most probably made of mostly ice and rock. And as the spacecraft Rosetta, which is a robotic spacecraft, there are no people involved, zipped past this asteroid, it saw that there were craters, and it even showed there's a crater chain, which was probably caused by a stream of meteors that were all related, falling onto the asteroid as it went by. So scientists are now poring over the images. The flyby is done. Rosetta is now off into the solar system. Rosetta will now pass by the Earth soon again, and it will also continue on to it will rendezvous in 2014 with that comet which I mentioned. Scientists will pore over the data and try to find out, for one reason, why this asteroid is so bright, and how this asteroid fits into the other asteroids that people know about. So 2 more images, and we only have 1 minute and 30 seconds to go. This is the Andromeda Galaxy, the largest, closest galaxy to our own Milky Way galaxy, which we reviewed last time when we were taking a tour of the universe. This is a satellite galaxy to it. This is M110, it's called. But the Messier catalog, which is what the M's are, didn't actually go up to 110. So we sort of added a new one. And since Messier isn't around, he can't be here to say don't do that. It also has an NGC number for new general catalog, which is 205. So this bright, small, dwarf elliptical galaxy, I believe it's a dwarf elliptical. I'm reading my own caption. Yes, it's a dwarf elliptical. Ellipticals aren't supposed to have much gas, but it has a little bit of gas here and here at 9 and 2 o'clock. So this galaxy may be gravitationally affected by the Andromeda galaxy. It might be eaten by that galaxy pretty soon. And since we're running out of time, we'll go to the next one. So this is today's image. This is from the Cassini spacecraft orbiting Saturn. There's some very, very small moons around Saturn. One of them is called Antha. I don't know if I'm pronouncing that right. And Antha is hit by micrometeors, we think, and creates a partial ring. And that partial ring is called an arc. So one of the things that the previous spacecraft, Voyager spacecraft, found out, and that the current Cassini spacecraft is finding out, is that there are rings around Saturn that are not complete rings. They're very faint, and they're centered on moons. And so that moon is in here. Antha is in here, and this is the Antha arc, and they're studying the extent of that arc and how it interacts with the moon to find out more about that moon and Saturn in general. And so that will wrap up a week's worth of astronomy pictures of the day. So next Wednesday, we'll start with the next 7, and next lecture, we'll get into the solar system and stars. So I will see you next time.